Welcome everyone to a presentation on 3D spatial visualization instruction within an introductory constraint-based CAD modeling course. This research was conducted between the fall of 2015 and the spring of 2018. We have contributors, 3 professors to this research. The first one is Dr. Ted Branoff. He is the professor and department chair of the Department of Technology here at ISU. The next professor that contributed to this data is Dr. Joshua Brown, and we have the next one is Dr. Kevin Devine. All 3 professors taught the Tech 116 course at one point. Dr. Brown is the current professor teaching the Tech 116 course, which this data is focused around. Lastly to note, the IRB, the Institutional Revenue Board, approved this research. Okay, so our first statement is our problem and purpose. The problem statement that was observed was some engineers and STEM professionals lack the proper training and experience in spatial visualization, and we'll get to what spatial visualization is. The purpose of this study is at Illinois State, some of the students are required or elected to take this Tech 116 course. The full name for the Tech 116 course is the Introduction to Technical Drawing and Constraint-Based Solid Modeling. This research assists in determining the validity of how it teaches spatial visualizations. The continuation of the problem and purpose is that we try to train proper engineers, overall like computer system technology students, the education majors in our department, the construction, and the overall population that takes this course. The objectives. So from their IRB submission, Brown and Branoff said they wanted to analyze the results to determine the effectiveness of our coursework in improving the spatial visualization skills of the students and contribute to the overall research of spatial visualization. And then they want to collect the data and see how it impacts the spatial visualization in the community by looking at different variables. They are determining the growth or deficiency of their Tech 116 students throughout the semester. So the research question and hypothesis. The research question is there an increase in students' spatial visualization skills as a result of taking Tech 116? The hypothesis is students will show a significant improvement from the start to the end of the course with their spatial visualization skills. Again, I'll go over the methodology, but the opposite of this would be the null hypothesis, which would be saying that students would not show a significant improvement in their skills, their spatial visualization skills. There's a couple assumptions and limitations. The assumptions are first, every student has access to technology. We're going to assume that they can come into the lab and get their work done. Scores improve from pre-test to post-test. That's a part of our hypothesis. We're going to have a quantitative data, and students can perform worse on the post-test compared to the pre-test. And students tried on both exams. The limitations. These students are degree-seeking college students. We did not contribute any research to 6th through 8th graders or 9th through 12th, so middle schoolers or high schoolers. And then not many research studies check the validity of a course. They check different socioeconomic status, different variables, and this is one of the initial researches that shows the validity of this course that's influenced. But there have been numerous research opportunities out there that have talked about the growth of spatial visualization from a pre-test and post-test using the same methodology that we have. And then another course interference is another limitation where another course that the student is taking could influence their spatial visualization skills, and we wouldn't be able to determine that. So our theoretical framework, we have course teaching and methodology materials. It's influenced by Sorby, Winsock, and Bartman, and that's from Branoff et al. Cheryl A. Sorby was from Michigan Tech. She did a lot of research within spatial abilities and engineering students. She determined and wrote research papers about spatial visualization within engineering students at her university. So we have Sorby's figure 1. She broke down these spatial skills into spatial visualization, spatial orientation, and then spatial visualization into mental rotation and mental transformation. As Sorby stated, that spatial visualization is mentally moving an object, while spatial orientation involves being able to mentally move the viewpoint when the object is in fixed space. Continuing mental rotation, it involves the entire object is transformed by turning in the 3D space. And then for mental transformation, there's only one part of the object that's being transformed. And this is all from her 1999 paper. So to continue the theoretical framework, we have from Wood et al. In 2016. The researchers stated that woodworking, Lego, 3D printing, welding, and sketching can influence the spatial visualization skills of students between when they start developing to when they're in college, when they take this course. All these can develop different foundations of their spatial visualization skills. So for the theoretical framework of LeBeau et al., they say that video games and computer games can influence construction toys, sports, drafting courses, as well as sketching. So they have similar between LeBeau and Wood et al. So this is methodology for the research in the Tech 116 course semester. So first we have the pretest. Then we go into isometrics, we go into rotations, we go into coded plans, Cartesian coordinate systems, orthographic projection, and then they have a quiz. After the quiz, they start getting into Autodesk Inventor, where they do CAD modeling, assembly, and section views, and then they have a quiz after that. And then they do threading and some other stuff. They have a final quiz. At the end, they do a final project. Involves the students building a Lego mechanism. And at the end, they have a final, going over all the material. And then at the end, from the second to last course, they have a post-test. Talking about the pre-test and post-test exams, we have the first test that we give for the pre-test and the post-test is the Purdue Spatial Visualization Test of Rotations, and it's usually PSVT. Next, we have the second test, which is the Mental Cutting Test, the MCT. Here's an example of the PSVT questions, one of the examples. So you can see that we rotate an object and they have to replicate that. And the Mental Cutting Test, we take an object, there's a plane in between, the students will figure out a shape and they determine what the shape looks like. And this all has to do with spatial visualization. We have a time constraint for each exam, still a part of the methodology. We have 20 minutes per exam, so 40 minutes. We have a pre-test at the second class. We have a post-test in the 31st class. Going on to data analysis for the PSVT, we can see that each of the exams are normally distributed. We have the blue, which is the pre-test, with a mean of 20.45, and we have the red dashed line, which is the post-test. And we can see that there is a significant increase in the scores, the mean scores of all the students. So that determines that the rotations taught in the class do help out with their spatial visualization skills. Moving on to the mental cutting test, we see both normal distributions but for the pre-test and the post-test. And again, we can see that there is a significant increase within the point values. From the pre-test to the post-test, there isn't a significant increase on both. We can see that the mean is 10.56 at 212.09. Since we have about 293 students in the population of our data, there is a one sample Z that is determined. And again, there's our mean and our standard deviation. And we can see that based on the confidence interval, we can see that both the post-test has a higher score than the pre-test with a 95% confidence interval. We could be 95% confident that the mean scores for the pre-test is between 19.8 and 21.1, less than the mean scores of the post-test. And for the mental cutting test, it's 10.0% to 11.1%. So to continue the findings, we have the dependent sample. So each of these are dependent samples monitoring the same groups of people at 2 points throughout the study. Each student is linked to a pre and post test, so both exams are dependent. Students take the two exams, one at the start of the semester to set a base, and the other at the end to determine the growth or decay of their skills. The improved scores depend on if students did better on the post-test than the pre-test. Based on the means, the overall population of students performed significantly better on the post-test compared to the pre-test. Moving on again to our other findings, we have the t-value of negative 5.42 for the PSVT and negative 7.65 for the MCT, which means that there's greater evidence against the null hypothesis. With many tabs stating that there's a p-value of 0, then the null hypothesis is also rejected. So the summary. With the 293 pre- and post-test scores taken between fall of 2015 and 2018, the different t and p values were observed. The t-value is further away from 0, so the null is rejected. The p-value is 0, so we reject the null hypothesis. Based on the quantitative data observed, the methodology assists in students learning the skills of spatial visualization. Therefore, the methodology should be replicated to different classes or schools. Overall, for better statistics on the methodology, reproducing the study can be performed. There's our references. Thank you for listening to this presentation.